This video defines the finite element project that we will be using ANSYS Mechanical to analyze. It is a 2D plane stress analysis of a plate with a circular hole under far field constant tension. Here, the main intent is to demonstrate stress concentration. It can be observed from the behavior of the animation of this plate that when a tension pressure is applied, a high stress, represented in red, is seen around the hole, called stress concentration. The goal of this project is to learn about finite element analysis, ANSYS Mechanical, and the effects of mesh and element type on results. Let us begin with the tutorial. Just as a bit of background, stress concentrators are geometrical irregularities, in this case a hole in the plate, which can cause an increase in the average effort that should be present in the regions near these discontinuities. The relationship between the maximum stress that occurs and the average effort that should occur is defined as stress concentration factor. A typical example of a stress concentrator is a rectangular plate with a central hole subjected to a tensile load, as shown in figure 1a. If the bar is cut in the cross-section of the hole, the tensile stress will be shown as in figure 1b. The stress distribution along the cut surface is substantially uniform until reaching the vicinity of the hole, where the efforts suddenly increase. The maximum value of stress at the points is found by multiplying the average effort by a factor of stress concentration. Now, let's look at the problem definition. Shown in the figure is the plate geometry and the loading that we will be looking at in the model for the project. A common modeling technique which we will employ is finding the symmetry in the problem and using it to simplify the model. Since the plate is symmetric about both the x and y axis, we can simplify the problem into one quadrant. To account for the symmetry, we will apply the constraints to the quadrant. For the y-axis symmetry, we constrain the left face so that it cannot move in the x direction. For the x-axis symmetry, we will constrain the bottom face so that it cannot move in the y direction. In terms of material properties of the plate, the Young's modulus is 10,000 ksi, and the Poisson's ratio is 0.3. The distributed tensile load on the top face is 1 ksi, kilopounds per square inch. The geometry has a length and height L, 10 inches. A radius of the circle being 1 inch, and thickness of the plate is 1 inch. In terms of modeling, we will subdivide the plate using both triangular T6 elements and quadrilateral Q8 elements with full integration. We will produce 3 models in 3 different cases of mesh and element types. Case 1, T6 triangular elements with a 0.5 inch uniform size. Case 2, T6 triangular elements biased from 0.2 inches along the bottom around the circle hole and 2 inches along the opposite face. And then case 3 being very similar to case 2 except using quadrilateral Q8 elements. The output for each case will be a plot of the stress over the quadrant, finding the maximum stress, then using the maximum stress to calculate the percent error of the model. The theoretical maximum stress of the hole is 3 ksi, which a perfect finite element solution would produce. The accuracy of the model depends on how close the model can come to producing this theoretical result. In terms of stress concentration, since the max stress is 3 ksi and the applied stress is 1 ksi, the stress concentration of the plate would be 3. At the end, we will produce results that look very similar to this. The next set of videos, we will introduce ANSYS, build the model, mesh, run, and get the results.